Modern vehicle diagnostic networks transmit data packets at a rate that demands dealership-level processing power directly in the field. The traditional service van operated on a simpler premise: transport wrenches, sockets, and heavy mechanical parts to a roadside breakdown. The layout in the rear of this specialized vehicle reflects a specific design priority. The volume of integrated equipment transforms the space into a dense, multidisciplinary laboratory. A technician's ability to perform advanced electronic repairs roadside is constrained heavily by the physical and electrical capacity of the workspace itself. Mobile operators face a dual physical challenge. They must carry heavy-duty recovery equipment to revive internal combustion engines, alongside high-voltage specialized tools required for electric vehicles. This physical layout centers on a third, highly sensitive requirement: delicate microelectronic programming and module cloning. To execute these diverse tasks safely off the grid, the van relies on strict architectural boundaries. We are going to map how this space isolates, powers, and executes complex hardware manipulation. Before a single diagnostic scan begins, the operator must actively manage power generation, as well as spatial limitations and environmental contamination. Writing new software to an engine control unit, or ECU, demands an absolutely stable voltage supply. A minor fluctuation can permanently corrupt the module. Pulling that power from the running engine of the host van introduces electrical noise and unpredictable voltage drops, creating an unacceptable risk of failure. To solve this, the operator relies on an independent power source. This image shows a low-profile solar array mounted tightly between the van's roof racks. Energy from the solar array flows into dedicated batteries. It then passes through heavy-duty inverters, converting the energy into a smooth AC sine wave. That power terminates at standard wall sockets, creating an isolated microgrid for precision bench tools. Inside the van, we see this physical integration. A vertical power strip with UK sockets sits directly above the workbench, supplying clean energy without interruption. Generating independent AC power is an absolute prerequisite. Without it, the risk of bricking a module during field programming is too high. Supplying stable power is only half the equation. The other half is spatial discipline. Triage across multiple fuel types demands extreme layout efficiency. Centered heavily on the floor space is a dedicated EV charging box, providing the substantial footprint needed to house electric vehicle rescue hardware securely. Yet, the operator must still address internal combustion engines, which require raw, high-amperage starting equipment. Located right at the rear doors for immediate access, two 12 and 24-volt jump packs sit secured on the floor. This layout follows a strict physical hierarchy. Heavy, dirty, and high-voltage equipment is restricted to the floor and lower bays. Gravity and placement prevent grease and grit from migrating upward to the work surfaces. Every tool occupies an engineered footprint based on its deployment priority and contamination risk, ensuring rapid access without compromising sensitive diagnostic areas. When a vehicle's native network is corrupted, technicians utilize CAN bus isolation. This requires physically removing a control module from the vehicle to test on a controlled bench. This workbench is the clean room for isolated diagnostics. A pass-through multiplexer translates data between the tablet and the raw module. The technician manually supplies power and network lines directly to the ECU's exposed pins, executing complex module cloning independent of the vehicle. Bench programming offers the most secure method for direct hardware manipulation. But executing it safely in a mobile environment is entirely dependent on the stable power grid and isolated clean space established earlier. Performing a successful ECU flash on the roadside involves a complex set of environmental variables that a standalone diagnostic tablet cannot address. The systems are completely codependent. The clean room requires the solar microgrid to function, and the heavy rescue gear requires strict spatial isolation to keep that clean room pristine. Vehicle network complexity and the total market share of electric vehicles on the road are both accelerating rapidly. Technicians who fail to scale up their mobile infrastructure will quickly find themselves lacking the physical and electrical bandwidth to diagnose modern platforms. As vehicle systems grow in complexity, a technician's capability is dictated by the architectural rigor of the mobile laboratory itself.